There we go. Brilliant. Okay. Okay, sorry about that. So, right, again, my name's Ben, and I work on GHC. And one of the things that Simon and sort of GHC, the developer community as a whole, has sort of concluded in the last, for the after having such a vibrant 8.0 release, is sort of let's devote 8.2 to sort of cleaning things up a bit. And shortly after 8.0, I think there was a bit of a discussion on Reddit, which pointed out performance in particular is, well, let's say you could use any of those adjectives up there, right? There's quite a number of things you can say about it, and perhaps one of the most unfortunate is that it does seem to be getting worse as releases go on. And, well, is that true? That's an interesting question. You can look at NoFib, and, well, things don't look, it's a mixed bag, right? So here we see NoFib performance. This is the geometric mean of the allocations and runtime for both the compiled programs, so the results that GHC produces, as well as the compiler itself, how much it allocates and how long it takes when compiling these test cases. And we see that, well, on the bright side, things do get a bit faster over time. This is actually quite nice, from 7.4 to 7.10, teens of percent in runtime. But yes, things are not good in the compiler side of things.
Is minus good or bad?
So yeah, this is relative. So this is relative to 7.10. Note. So this is sort of the baseline. So here we see that allocations, for instance, allocations increased by around 30% from 7.10 to geometric mean, and 7.10 was 26% worse. Be careful, I guess. Yeah, then.
Minus is
No,
both
I
good.
don't.
7. Yeah, anyways, yeah. So right. So this is not a good story. So why is it? Well, where did we go wrong? And so these numbers are obviously not going to provide us with the sort of temporal resolution that we need to resolve this and to answer this question. NoFib. These NoFib runs, release per release, are great, but we really need something that will give us a bit more insight into where and how things are regressing. And this is a tool that, so with this in mind, I sort of set the task of, well, what would I want to really track performance? And really, we have a nice time series, an incredible set of time series data that Joachim has actually been collecting for around, I think, 2 years now, for his Pita GHC speed instance, where he builds every commit, runs NoFib on it, and saves the logs. And so I started by simply slurping all this data into a Postgres database. It's a form that I could easily query, find trends in, and started hacking around in Python, and ultimately ran into some, it simply it did not allow me to iterate quickly enough. And so I wrote this rather unholy mess of Haskell and JavaScript. And this is what I call Pita, the performance indicator tracking application. And so ideally I would like to demonstrate it. Unfortunately, the computers aren't going to cooperate here. But so what we see here in this rather blurry, low-resolution image is a time series. This is on the x-axis is this time. This is number of commits this is the master branch, if you can squint a little bit. And what we see here is, down the left-hand side, we have the set of metrics that NoFib collects. And we see a bunch of curves, one for each. There are check boxes here, and you can select a subset of the metrics that you're interested in, plot them over time, and you see these are all allocations, compiler allocations for compiling various NoFib metrics, and we see a few things that you can kind of glean, even with this rather low resolution image. We see that over time the GHC, there's sort of two trends here. There's sort of a gentle upward slope, and then there are these very large, punctuated by these very large steps. And well, when I saw that, I was quite excited, because that means, well, if we can just knock this one down, if we can figure out what happened there, then we can immediately, that's a significant improvement. Whereas if it was just a sort of summation of a bunch of, thousands of tiny little steps, each commit regressing by a fraction of a percent, then that's a much harder problem. So, and so in the below here we have the sort of largest changes in each of these cases, and these are these labeled commits here. These are actually commit SHAs. And so you can look and say this is in 2008, we had this commit which regressed this test by negative 19%, and the commit title is that. And so it really gives you a great way to very quickly gain understanding into the performance characteristics, the dynamic characteristics of no-fit performance over years. And this is in contrast to Pita, which is a really fantastic tool for looking at, did my most recent commit regress? But as far as identifying particular points over the last year that regressed, it kind of, it's a much different problem. So, let's see. So the typical workflow, and so with this tool in hand, I started doing a few comparisons. The first question that sort of came to mind is, we often say that are allocations actually, do they correlate well with runtime? How well does this correlation work? And actually, of course, we would like to be able to measure allocations and pretend that's a perfect proxy for runtime, since runtime is just terribly noisy. And I found that I would like to demonstrate it to you. Unfortunately, can't do the demo. But runtime, in fact, does follow allocations most of the time. There are cases where you see rather measurable jumps in allocations without a corresponding jump in runtime, or a much smaller jump in runtime. So it is actually important, and this tool makes it easy to, before you take for granted that a jump in allocations is going to result in a jump in a regression in compile time. It's good to check this, and this is something that this tool makes quite easy. And as I said before, regressions are generally easily recognizable discrete jumps, which is great for those of us who want to optimize the compiler. And so, sort of having a rough qualitative understanding of this data, sort of went ahead and started actually looking at particular cases, cases where allocations jumped significantly and there was a corresponding jump in runtime. And found, looked for strongly affected no-fib tests, tried to find the largest change that I could for a particular commit, a test that regressed most strongly. And then I found that in the profiler, our cost center profiler, is a great tool, but it is, for GHC, rather painful to apply in optimizing the compiler, because you either have to optimize most of the compiler, or by default, you only have a few cost centers sprinkled about if you ask for a profile GHC build. And this is and moreover, you have the problem of the costs change in the profile build. So I actually, more often than not, used the Tiki profiler in my comparisons, built a pair of compilers, one before the regression and one directly after, and both with Tiki instrumentation, and compared the Tiki profiles with some tooling I developed, which is available, and just tried to chase down what was allocated and where, and started just looking in that vicinity and tried to understand where the allocations, why the allocations now occur where they did not previously, and head impacts wall, and repeat again and again and again until you finally think you understand what's going on. Bang your head against the thing for days and days and days, and eventually you end up finding that things actually improve. So I would love to show you the plot, current state of performance. It's actually a rather nice plot. So after solving around two major issues and a few more minor allocation regressions or decimal implementations, I found that we could actually bring down, without that much work, allocations by around 15 or so %. Runtime is sort of comparable, and many of runtime changes comparable. And all of this because we now have insight into the runtime characteristics over time. And it really, I cannot imagine having been able to find affected commits and regressions so quickly and be able to actually solve them so quickly without seeing that plot and getting this. So there's some future work. Need to GHC 8 as of 8.0.1. We now have the ability to actually time individual compiler passes. This is very helpful because it allows you to sort of immediately narrow down on what part of the compiler has regressed. There's some work to be done here to ensure that these numbers actually reflect the costs within the compiler, but at least the infrastructure is there, and we just need no fib to record it, and so we can better account for this. And then we also need more performance test cases, and this is where I think if you are even not a GHC developer, if you don't know the first thing about the internals of GHC, if you're a GHC user, please, I beseech you, if you find your program is regressing, please send it to us, and if at all possible, in minimized form. Yeah, the groans are, I understand, it's not fun. But even...
Do you mean that if you find that your program is compiling more slowly than before?
Yes.
I mean if it's running more slowly?
Well, either, I suppose, but in this case, I would like to, compilation, especially in the case of compiler performance regressions, minimized test cases are incredibly useful. And keep in mind, so I have a carrot to offer here. If you do send us a minimized test case, it will go into no-fib, and your program will not regret. We'll try very hard not to regress your program in the past, because now we can actually measure it. So if you do care about your program's performance, then it's in your best interest to minimize and send it in, and you will not regret it. So let's see.
About computing compile time per token. I was thinking of some so maybe some programs are kind of weird and take a lot more compile time per unit of program size than others.
Oh, of course.
And lines of code is a bit flaky because of comments and how long your lines are, but maybe per lexical token would be a crude approximation.
Yeah.
Say if your megabytes per token is bigger than this.
That's a fair point. Yeah.
Should sort of maybe GHC should even say, this program appears to have high megabyte per token ratio.
Yeah, that's an interesting point. That's yeah. So I mean, there are various. Well, anyways, and moreover, we do have a performance test suite in GHC. We have in our test suite there are test cases which are particularly checked for compiler statistics such as runtimes and allocations. Allocations. But this is a mechanism that I think really needs to be revisited. It really causes undue burden for the amount of benefit that it gives us. Updating these numbers happens intermittently and not at the times when you'd like, not at the times where the costs actually change. So we need to figure out a better way of tracking this performance, expected performance number data.
Sorry, I got a question.
Of course.
Are there any broad categories of issues that you encountered, or are those completely unrelated things that
I was
the runtime slowdown?
Yeah. So I was hoping to have a nice answer for you there. There was a nice theme to these issues, but unfortunately, for better or for worse, it really was just a smattering of issues scattered in various places. So from serialization performance of the sort of low-level serialization primitives to the type checker, we have broken laziness in the type checker, and so it's actually interesting to note that the issue, the commit that actually led me to find the type checker laziness issue had nothing to do with the compiler. It wasn't even in the compiler, it was in base. And so you really need to, when looking at these issues, I would spend a long time trying to work out why why this particular change in base would affect the compiler, where it really was actually in the compiler itself, and that was the compiler's costs were not in alignment with my cost model that I had. So keeping an open mind is important when looking at these issues. Right, so we need to find a better solution for keeping track of expected test numbers. Right, I'd like to, again, recognize Joachim for his Pita, and especially the work he's done in building these commits and gathering this data over time. It really was invaluable, and this is something that is going to become more and more important as hopefully in the future we can get more people to report observed regressions, both in compiler performance and in compiled code performance, but and contribute minimized regressing code samples, and then hopefully we can get developers better into the feedback loop of how compiler performance is behaving over time with tools like Pita and Joachim's building. So thank you.
I think we'll just give it a few more minutes because of technical problems, so we have time for questions, I think. So
you regressed by about 30% from the figures at the start.
Yeah.
And you recovered about 15%. Is there hope that we'll get back?
Oh yeah, no, I mean, so this is by no means done. I still have patches in flight, which I believe, at least, it's not done until it's done. The patches don't validate, but so far with the non-validating patch, I do see improvements in compiler allocations in the test suite, so that's a good sign of test 10% in one case. So that's a good sign, and I think really we just need more people to, if you have time, if you want a nice problem. We're going to try to get a Pita instance running on GHC infrastructure so that anybody can browse these numbers. Just look at these, find a nice bump, and just go to town. I think there's a lot. We just need more eyes. But I'm going to also continue to look at this.
If you're not targeting a specific patch, increase compile time, you have other ways of, if you want to proactively improve performance, you have ways to handle that.
Yeah, that's a hard. Ultimately, that's a hard thing to do. I think you need to have a very good understanding of what the compiler is doing in order to reason about how much you would expect a certain program to cost in compilation. And I personally, I don't think I have that. I think it would be very difficult. I think it's much easier to identify. This is why I went with this route, because I think a priori it's very difficult to know how much a particular program will cost.
Is the startup time of CI already being tracked?
The startup time.
Yes, because that has been the regulation by ICFP from the for small scripts.
Oh yeah. So I think I probably have an idea of why it's so slow. Yeah, the dynamic linker. It's how we use dynamic linking, and it's something that we can solve relatively easily. But so we don't have a zero compile time runtime test. That's a good point, though. I mean, we should have a test that measures this.
Right.
Great.
Thanks, Ben.
Thank you.